Okay. So let's do this thing. All right, so this one is, all right, so the primary functional group is this alkene. So then this is called 4-tert-butoxy 1-cyclohexone. Like alcohols, ethers have nearly the same geometry as water, approximately a tetrahedral bond angle. Okay, the electronegative oxygen atom gives ethers a slight dipole moment, and the boiling points of ethers are often slightly higher than the boiling points of comparable alkanes. Okay, cool. Honestly, I'm not too interested in that. Ethers are relatively stable and unreactive in many respects, but some ethers react slowly with the oxygen and air to give peroxides, compounds that contain an OO bond. The peroxides form low molecular weight ethers such as diisopropyl ether and tetrahydrofuran. Okay, wait, I understand what they're saying. The peroxides from low molecular weight ethers, such as diisopropyl ether and tetrahydrofuran, are explosive, even in small amounts. Ethers are very useful as solvents in the laboratory, but they must always be used cautiously and should not be stored for long periods of time. Yeah, I've read that. Okay, whatever. Name the following ethers. Let's do it. So we get C, 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 O, C, C. All right, so that was diisopropyl ether for sure. Okay, B looks like it's going to be propyl cyclopentyl ether. C is going to be, so is this considered another functional group or no? I think it would. I think it would be called 1-bromo 4-methoxybenzene. So this one would be called 1-methoxy cyclohexone. 1-methoxycyclohexone. Okay, that's at least what I think it is. Let's see what the hell this is. So we got an ether, and then I think there is a special name for this, but I would just call this 2-methyl-propane. So ethyl 2-methyl-propane ether. I don't know if that's right. Ethyl 2-methyl-propane ether. I mean, it seems like it makes sense, but is it right? All right, here we have alkenes. I don't know, can I just name them? So this is going to be like ethene, and then where do you have to number it from? Do you have to number it from here? Probably not. I would assume you don't. So then I'd call it ethene propene ether. Yeah, I found out this textbook has this awesome student solution guide. Like before the textbook answers, they didn't even have the end of book answers. And it was driving me crazy. Wait, this is the wrong one anyways. So we need to go here, books, student solutions. Chapter, what are we on, 18? Okay. But it is homework, and I don't understand this epoxy stuff, or epoxide stuff. I know how to do this one. I think you use Lindlar's, and then you add, like, ozone or potassium permanganate. I think it's potassium, no, it's osmium tetroxide. But anyways, you get a syndiol. And then this one's pretty easy, too, for the mechanism. But I don't know how to move the alcohol. I don't know how to do this. I don't know how to do pretty much any of these. It's called alkynes homework, but it's like, is this really even alkyne homework? Yeah, let's look at the answers though. Okay, diisopropyl ether is right. Oh, geez. Oh, no. Okay, so they also said propoxycyclopentane. So we could also call it propoxycyclopentane. But I said propylcyclopentyl ether, which I don't know what the order is. The order, actually, it's probably alphabetical. Yeah, it's alphabetical. So it would actually be okay. Then C. It said parabromomethoxybenzene. I think it would be equivalently fine to say, let me actually do this too. Yeah, oh wait, what? Why did this become the main? Did the precedence orders are weird? So I put 1 and 4 instead of 4 and 1. Okay, D is, I put 1-methoxy cyclohexone, which I think is fine. Okay, I didn't do the isobutyl, but that's fine. Ethyl. Wait, ethyl. I don't think that's right. I'm pretty sure this is wrong. Because if you look at it, it has a double bond. Oh, wait, no, this one. Wait, no. Oh, I'm looking at the wrong one. Oh, wait, now I'm confused. Oh, I think what you're supposed to do is you're supposed to do F in ill, right? Aren't you supposed to do ethanil to make it a substituent name? Okay, in any case, we're looking at the answer for, we just did D, no, E. I said ethyl 2-methylpropane ether, which is probably fine. I mean, this is allyl vinyl ether. What the hell is that? That's ridiculous. Okay, that one's stupid. Allyl vinyl ether. Bro, that's so stupid. Allyl vinyl ether. You gotta be kidding me. Alright, preparing ethers. Diethyl ether and other simple symmetrical ethers are prepared industrially by the sulfuric acid catalyzed reaction of alcohols. The reaction occurs by SN2 displacement of water from a protonated ethanol molecule by the oxygen atom of a second ethanol. Unfortunately, this method is limited to use with primary alcohols because secondary and tertiary dehydrate by E1 to make alkenes. Alright, let me look at this reaction. So here we go. Ethanol, protonated, oxonium, and then a second ethanol attacks this okay, and then this leaves, but then we're left with this, and then water dehydrates this. Okay, or dehydrogenates this. I don't even think that's the right word. Honestly, it's so hard to keep track of the hydration, hydrogenation, hydro. Okay, so let me write this mechanism. This mechanism is pretty interesting because if you wanted to make diethyl ether, this is how you would do it. This is how they do it. So we have CH3, CH2, OH. And then we have H3O plus. The oxygen attacks a proton to take it, and then we get CH3, CH2, oxygen, H oxonium, this plus. And then what happens here, though, is that we have another one come in here, attack the carbon, pushes off the water, so now we're left with CH3, CH2, OH, CH2, CH3, and water. And then water's oxygen comes and takes the proton off again. And we're left with diethyl ether and H3O plus. That's pretty cool, but it seems like the kind of thing that you can't really do at home. I don't know why, but like if I just put a bunch of sulfuric acid and ethanol together, is it going to do this? Ooh, this is good because I was just looking up how to make anisole, and people said that this is how you got to do it. All right, so Williamson ether. The most generally useful method for preparing ethers is the Williamson ether synthesis, in which an alkoxide ion reacts with a primary alkyl halide or tosylate in an SN2 reaction. As we saw in 17.2, an alkoxide ion is normally prepared by reaction of an alcohol with a strong base, like sodium hydride. Alright, so let's draw this out. Alright, so we have cyclopentanol reacted with sodium hydride in THF. Now what happens is that this hydride, so this H minus, is going to come and take this proton, and then we're going to be left with O minus. So this is the alkoxide. So this is the alkoxide ion. Okay, and then what we're going to do is we're going to react this with some alkyl halide, like iodomethane. And what's going to happen is that the lone pair here is going to SN2 it. I like this mechanism. Williamson ether synthesis. That's a pretty nice mechanism. The only thing is, how expensive is this stuff? I bet this is extremely hygroscopic. 10 grams for $60 is actually not that expensive. Superconducting? What? Look at the dry one. That's crazy. What's an imine again? I don't remember. Alright. It's not important. 74% is pretty good. The useful variation of Williamson synthesis involves silver oxide as a mild base rather than sodium hydride. Under these conditions, the free alcohol reacts directly with the alkyl halide, so there's no need to perform a metal alkoxide intermediate. Sugars react particularly well. Glucose, for example, reacts with excess iodomethane in the presence of silver oxide. I didn't really understand what that was about. Okay. Because the Williamson synthesis is an SN2, it is subject to all the usual constraints as discussed. Primary halides and tosylates work best because competitive E2 elimination can occur with more hindered substrates. Yeah, especially with something so strong, because I'm pretty sure sodium hydride is a really good base. Okay. Unsymmetrical ethers should therefore be synthesized by reaction between the more hindered alkoxide partner and the less hindered halide partner, rather than vice versa. For example, tert-butyl methyl ether, a substance used in the 1990s as an octane booster in gasoline, is best prepared by reaction of tert-butoxide ion. Yeah, they're just saying because there's no way you'd be able to do SN2 on this thing. That's all they're saying. What is this? Oh, and here they're just saying you end up with an ether because there's no way that you're going to get a It, wait, what did I say? Alkene, not ether. What? Alright, why do you suppose only symmetrical ethers are prepared? Why do you suppose only symmetrical ethers are prepared by the sulfuric acid catalyzed? Bro, I don't know. Okay. Why do you suppose only symmetrical ethers are prepared by the sulfuric acid catalyzed dehydration procedure? What would you expect if ethanol and 1-propanol were allowed to react together? That's right, we have ethanol and 1-propanol. Do they even give me a mechanism for the acid catalyze? Yeah, okay, so I was right about that, and then this guy comes in here. I actually don't know. Oh, bruh, obviously. Yeah, that's because. Yeah, okay, that makes sense. So, yeah, so this basic mechanism is nice, but it's not very good because you can't make unsymmetrical ethers. That's cool. Okay, methyl propyl ether is just going to be. Actually, I guess I should be drawing like this. So we allow ourselves to have access to alkyl halides. So what we're going to do is, this is the easiest one. We're just going to take propanol. We're going to add NaH to it in THF. And we're going to get propoxide ion. So then the propoxide ion, we're going to react with methyl or iodomethane, or let's say bromo. Let's mix it up with the halogen. Okay, that's pretty simple. So the answer is I would react and I would say that the propanol group is more sterically hindered. So I want to start with that alcohol rather than start with the methyl alcohol and try to do SN2 on a because it's still gonna work because it's a primary carbon, but the methyl isn't even a primary carbon, it's just a methyl carbon, so it's like the least sterically hindered of all. So yeah, so you're going to start with taking propanol, reacting it with sodium hydride. That's going to deprotonate the alcohol. Then you're going to have a propoxide ion. Then the propoxide ion is a good nucleophile for SN2. So then you react it with, some halo methyl group, like iodomethane or bromomethane. And SN2 will happen, and then you get your ether. Okay, that's chill. I like that a lot. Alright, anisole, which is methyl, phenyl, ether. So we want to start with phenol, obviously, because it's going to be a secondary carbon, and there's just no way that SN2 is really going to happen that well. So we have phenol. We have phenol. Do the deprotonation with the sodium hydride in THF, and we're going to get the phenoxide ion. And we're going to react that just with, again, something like iodomethane. And we're going to finally get our anisole. So yeah, so this would be fun to do, but phenol is a little nasty, I think. I'm pretty sure phenol is pretty nasty stuff. Okay, here we're getting benzyl isopropyl ether. So here we're going to draw the benzyl group. And then we're going to draw the isopropyl group. And we can see that the benzyl group is actually wait, no, I messed up the drawing. This needs to be like this. Is a primary carbon, but the isopropyl group is a secondary carbon. So we're going to start with 2-propanol or isopropanol. I prefer 2-propanol. So we're going to say 2-propanol. And react it with the sodium hydride to deprotonate some strong base. And this H just comes in, or this oxygen. Wait, what's the mechanism for deprotonation? Actually, wait, am I tripping? How does this thing deprotonate? I swore I drew it. You have an H minus. What does the H minus do? I think does it just form hydrogen gas? Yeah, so it just makes H2 gas. Okay, that's what I thought. Okay, cool. Yeah, so that's good. Okay, so the hydrogen gas forms, and then we're left with 2 propoxide ion. And then we're just going to give it a benzyl. What do we call it? Iodo. What do you call? Iodobenzene? Benzyl iodide. Okay. Okay, so this comes here in SN2's this thing. Okay, that one's pretty good. I like that. Okay, now here we go. Ethyl 2,2-dimethyl-propyl ether. Okay, so let's just write ethyl is like this, and propyl 2,2-dimethyl. Okay, so what we want is then like an O here. Okay, so clearly, bro, this one's like it's the same difficulty as the last one. It's that the 2,2-dimethyl-propyl is like tertiary. So obviously, I'm gonna do this. So this is gonna be like tert butoxide. So NaH takes the proton, forms H2 gas, and tert butoxide. Then we're just gonna have ethyl. Do you call it iodoethane? Ethyl iodine, ethyl iodide, and iodoethane are the same. The common name is ethyl iodide, but iodoethane is the. Yeah, that makes sense. Oh, okay. So for benzyl iodide, it's actually iodomethylbenzene, which I prefer. That's fun. All right. Did I check my answers though? I'm pretty sure they're all right, but let's just do them. Well, how did the book answer it? Phenoxide, methyl, iodomethane. Okay. Now here we go. Here's the more hindered. And then here's the benzyl iodide or whatever, halo, benzyl halide. D. Yeah, here's this tert butoxide, I think. And then just the bromoethane or whatever. Interesting. Okay. Dude, I gotta finish this. The homework is due tonight. Let's see, how much longer is this section? I bet it's so long. I wouldn't doubt it. Actually, it's not that long, because I'll skip this. I'll probably skip thiols and sulfides. Definitely need to do up to here, though. And probably even this. We saw in section 8.4 that alkenes react with water in the presence of mercuric acetate to yield a hydroxymercuration product. Subsequent treatment with sodium borohydride breaks the C-mercury bond and yields the alcohol. A similar alkoxymercuration reaction occurs when an alkene is treated with an alcohol in the presence of mercury acetate or mercuric trifluoroacetate. Demercuration by sodium borohydrate then yields an ether. The net result is Markovnikov addition of the alcohol to the alkene. Okay, here we go. We got an example. Okay, so styrene. Okay, so yeah, I understand. Whoa, 100%? That's freaky, man. Okay, so 18.2, right? No, we're just in alkoxymerc. Okay, so yeah, here we go. So, okay, and then step 2, so this is 1. And what's the solvent? Water? Yeah, solvent is water. And then the second is just the sodium borohydride. And what we get is all right, so yeah, so we add water across it. And now just like we did this to the moist substituted carbon, we're going to add an alkoxy, which is, RO minus. We add RO minus in a Markovnikov way. So that's cool. So here, let's do an example. So we're going to get this styrene, carbon, double bond, carbon, and then there's one hydrogen here, and 2 hydrogens here. So this is a secondary, and this is a primary, and we're going to add this special reagent. It's a better mercuric acetate, and it's, what is it called? Mercuric trifluoroacetate. Mercuric trifluoroacetate. And we're doing it in water? We're doing it in methanol. Oh, so we can, yeah, because we can use, but don't we need an acid to deprotonate it? I don't know. Anyway, so this is called CF3 CO2 2HG. And then we do it in our CH3OH. And so what we end up with
last time I saw them, it was like did exchange it on us, so like figure code in and they will.
They should for sure change that. Prices are going up. They're but and even the time to have they change. It's hard to keep your input costs right. So this really is what involves
and that's 97% yield. So that's insane. I wish they had a citation here where you could click on it and be like, how did they do that? 97% yield is crazy. So this is step 1. And the step 2 is just normal sodium borohydride. Which, I don't even remember. How expensive is sodium borohydride? It's not terrible. All this stuff is like $100 for 100 grams. It just always ends up that way. I don't know why. Okay, I'm never going to remember this thing. I'm just going to write. Does it only work with primary and, does it only work with primary? It didn't say if this is SN2. The mechanism of the alkoxy-mercuration reaction is similar to that described in 8.4. The reaction is initiated by electrophilic addition of H2 to the alkene, followed by the reaction of the intermediate cation with alcohol, and reduction of the CH by sodium borohydride. A variety of alcohols and alkenes can be used in alkoxy-mercuration. Primary, secondary, and even tertiary alcohols react well. Oh, interesting. But di-tertiary ethers can't be prepared because of the steric hindrance. That's one of those ones I just want to look at the answer for. Right, so this mercurinium bridge or whatever. Mercurinium bridge. Then the alcohol attacks. Opens this up this way. That's why I'm pretty sure it has to be anti-addition. And then the base takes a proton. And then okay. Alright, so that's pretty chill. This is, dude, I freaking love that I found the student manual, man. It's so sick. Okay, how would you prepare the following ethers? Use whichever method you think more appropriate. Williamson. Bro, there's so many mechanisms that I've gone over today that I can't stuff any more mechanisms in my brain. Okay, so Williamson is just like SN2. It's form an alkoxide and then do SN2 with that alkoxide on some alkyl halide. And alkoxymercuration is use this special reagent to specifically get, and I don't think a carbocation forms, right? Yeah, wait, hold on. Yeah, we don't get any rearrangement, but oh, I forgot about this. I don't even remember that.
I'm using your iPad.
What happened? Okay, here we go. All right, so no rearrangement occurs, but presumably, let's see. Actually, in Williamson ether synthesis, no carbocation forms either, so there's no rearrangements because it's SN2. All right, let's do this problem then. 18-5. How would you pair the ethers? Butyl cyclohexyl ether. Okay, so butyl. I think that because I feel like the best thing is just to do take cyclohexanol and do the Williamson ether synthesis. I think that makes the most sense. And then we're gonna just take iodobromane, bromane. What the fuck? Iodobutane, bromane, and then we're just gonna attack. So that's the easiest way for that one. Benzyl ethyl ether. Okay, so benzyl. Is there any reason not to just use Williamson. Like when do you not use Williamson? Yeah, I think that the second one is also Williamson. Right now, sec-butyl. What does that even mean? Sec-butyl, tert-butyl. I forget what the difference is. Yeah, I kind of hate that. I feel like that's like a, but whatever. I don't care. All right, so it's sec, butyl, tert, butyl. Is that for me?
No, I just wrote it under showing you.
All right, sec, butyl, tert, butyl, ether. So this is gonna. So let's just do the tert butyl first. Okay, so I think this might be the case where you need to do oxymercuration. Because I just don't think SN2 would give you a good yield. So in that case, what do you do? How the hell does this work? If I did, Dude, I don't know how to do this one. Yeah, use alkyl oxymercuration because both parts of the ether are branched. Okay, so they're saying C, 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 double bond. Okay, and then by adding these reagents, and so here, this is the one that we need to figure out. Oh, this is the sec butyl. Okay, so then we're going to do plus OH bonds to sec butyl, which is CH3, CH2, CH2, CH3. So this is the sec butanol. And so this under the, I'm just going to say oxymer. It's like some insanely long, like who's going to remember this? I'm not going to remember this. But okay, that one's pretty good. Now let's see, why does Williamson need to be used for this one? Tetrahydrofuran. Why? Oh wait, actually, hold on. So let's just say that we had okay, let's say that we had one iodo. Oh wait, is that right? No, I think we want to call it four iodo. 4-iodo butanol. 4-iodo butanol reacted with the NaH. And then there's an internal SN1. That's pretty sick, actually. That's pretty sick. The ring closure, dude. Alright, I really like that one. Internal ring closure. Dude, I gotta hurry up, man. This is not good. Rank the following halides in order of the reactivity in the Williamson synthesis. I would assume 1, 2, 3. bromoethane, more reactive than 2-bromopropane, which is more reactive than bromobenzene. Ooh, part B is interesting. Chloroethane, bromoethane, and 1-iodopropene. What does this look like? Wait, it said propene. Bro, what? 1-iodopropene. Why is that not a chemical? Okay, cool. So I would assume I actually have no idea. Alright. Reactions of ethers, acidic cleavage. Ethers are unreactive to many reagents used in organic chemistry, a property that accounts for their wide use as reaction solvents. Halogens, dilute acids, bases, and nucleophiles have no effect on most ethers. In fact, ethers undergo only one truly general reaction. They are cleaved by strong acids. Aqueous hydrobromic acid and hydroiodic acid will both work well, but hydrochloric acid does not cleave ethers. Okay, so which side does it cleave on, though? I'm gonna get my hoodie. Well, that's not really your Okay. Um, Acidic ether cleavages are typical nucleophilic substitution reactions and take place by either by SN1 or SN2 mechanism, depending on the structure of the substrate. Ethers with only primary and secondary alkyl groups where it reacts with the protonated ether at the less hindered site. Ethers with tertiary benzylic or allylic group cleave. Ethers with the tertiary benzylic or allylic group cleave by SN1 or E1 mechanism because these substrates can produce stable intermediate carbocations. These reactions are often fast and take place at moderate temperatures. Tert-butyl ethers, for example, react by E1 on treatment with trifluoroacetic acid. Tert-butyl cyclohexyl ether with this dang reaction again. Or wait, actually, this is something else. But this is like kind of like this trifluoro thing is interesting. What's the mechanism? Bro, it's like so obvious. This is gonna have the OH, and this is gonna have this is gonna be bromopropane. Wait, what? Wait. Okay, this gets protonated, right? So there's an H here. Now this is gonna be way too hard for the bromine to attack. So the bromine has to attack this one, pushing the thing over. Oh wow. Okay, this is getting complicated. Recall the guidelines for ether cleavages. An ether with only primary and secondary alkyl groups usually undergoes cleavage by SN2 attack of the nucleophile on the less hindered alkyl group. But an ether with a tertiary alkyl group usually undergoes cleavage by SN1. Oh, so SN1, so this is going to give up the electrons and form a carbocation. Okay, I get it. Okay, I get it. That's actually pretty interesting. Dude, I've done so much chemistry today. It's crazy. I'm slamming the chem today, bro. Yesterday kind of too, but today's just been all chemistry. Chemistry is pretty interesting. You know what I mean? All right, so predict the products of the following reactions. So here we have a tertiary carbon and a primary carbon. So in hydrobromic acid, tertiary, it's going to do SN1 because I guess it does. Honestly, that whole thing seems pretty ridiculous to me. Because I feel like this would attack and this would immediately attack back. Anyways, this attacks, this becomes a positively charged oxygen. And then basically what happens is this just voluntarily kind of gives up the electron pair, forming methanol. And now we have a carbocation here, but this is tertiary, so this is probably not going to rearrange, right? I would not expect this to rearrange. So then the bromine just attacks here. So what I would get is, let's see, let's draw this phenyl ring. So what do you call this? What do you call that? I actually want to name that. They probably give me the name. And then methanol. Okay, so this is A, B. Here we have secondary to primary, so this is going to go SN2. Or, yeah, secondary to primary. So but what's going to happen here is this is less sterically hindered. The bromine's going to go in here. So we're going to get, I don't even know what you call this. It's just going to be CCC COH. And we're going to get then bromo propane. But what do you call this? It's going to be called 1-methyl propanol. Oh, no. Wait, is it? Or is it going to be called butan 2-ol? That's what I think it's called. 2-butanol. I'm pretty sure that's what it's called. Let's see. Am I right? This is 7. They didn't give me the name of it. Two bromo 2-phenyl propane. Okay, that kind of makes sense. If I thought about it for a while more, I would have gotten that. I'm not even going to say that. All right, let's go. 18.8. Write the mechanism for the acid-induced cleavage. Write the mechanism of the acid-induced cleavage of tert-butyl cyclohexyl ether. Okay, so first let's just write tert-butyl cyclohexyl ether. To yield cyclohexanol and 2-methylpropene. Wait, 2-methylpropene. Oh yeah, okay, yeah. This is so what we're gonna do is we're gonna add hydrobromic acid. The oxygen lone pair is gonna attack it, and then what's gonna happen though is because the tert-butyl group is tertiary, the lone pair is gonna go on to this thing, and when a lone pair goes onto it, it's gonna form a carbocation here, and that's where we're gonna get the bromine. But what happened? Where is this? Where the hell is this alkene coming from? That doesn't make any sense. It almost makes sense, but it doesn't. Why doesn't it just... Wait. I'm tripping. Yeah, 2-methyl. This bromine is not 2-methyl. Oh, they're just saying write the mechanism. So if I'm given that forms, I'm not saying what's the major product. I'm just saying... Okay, so here, carbocation forms. Okay. Dude, I saw projects in flight make this. This is pretty cool. I forget why he needed it. I've seen a couple other people make 1,4-dioxane. It does look like a pretty cool chemical. For the most part, cyclic ethers behave like acyclic ethers. The chemistry of the ether functional group is the same whether it's in an open chain or in a ring. Common cyclic ethers, such as tetrahydrofuran and dioxane, are often used as solvents because of their inertness, yet they can be cleaved by strong acids. The one group of cyclic ethers that behaves differently from open chain ethers are the three-membered ring compounds called epoxides. The strain of the three-membered ring gives epoxides unique chemical reactivity. Ethylene oxide, the simplest epoxide, is an intermediate in the manufacture of both ethylene glycol used for automobile antifreeze and polyester polymers. Oh wow. Wait, can you just buy it? Is it stable? Can we just buy this? It's pretty expensive, but you can buy it. Approximately 37 million tons of ethylene oxide is produced worldwide each year, most of it by air oxidation of ethylene over a silver oxide catalyst at 300 C. This process is not useful for other epoxides, however, and is of little value in the laboratory. Note that the name ethylene oxide is not a systematic one because the "ene" ending implies the presence of a double bond. The name is frequently used, however, because ethylene oxide is derived from ethylene by addition of an oxygen atom. Other simple epoxides are named similarly. The systematic name for ethylene epoxide is 1,2-epoxyethane. Okay, cool. Okay, that's a cool name. Alright, so they usually call, so common name, wait, I need 18.4. Okay. Cyclic ethers, epoxides. So the common name for C bond CO H3 H3 is called ethylene oxide with IUPAC name 1,2-epoxyethane. That at least makes more sense than ethylene oxide, which makes no sense. Epoxides are usually prepared by treatment of an alkene with a peroxy acid. That's right. Yeah. I saw that earlier today. Peroxy acid. Where did I see that? Oh, here we go. It was in forming a transvicinal diol. On a ring. Okay, in any case. Oh yeah, here we go. MCPBA. Metachloroperoxy metachloroperoxybenzoic acid in DCM Epoxides can also be prepared from halohydrins. I forget what halohydrins are. Epoxides can also be prepared from halohydrins, themselves produced by electrophilic addition of chlorine gas or bromine gas to an alkene in the presence of water. I forgot what that mechanism is. It's this one, halohydrin formation. Okay, so this is a halohydrin because you have a trans vicinal halohydrin or hydroxyhalide. I don't know what the hell you're supposed to call this stuff anymore, man. It's all in one ear and out the other. Okay, when a halohydrin is treated with a base, HX is eliminated. And okay, and an internal SN2 happens. That's right. Oh wow. So okay, so we used to just call it intramolecular SN2. Now we're saying it's intramolecular Williamson ether synthesis. Okay. We'll get the heater. I'm cold. We got chat. What's up? Hey, I find your showing this. What is your major and minor? My major and minor is ligma ball. All right. 1810. What product would you expect from reaction of trans-2-butene? Okay, so trans-2-butene with which is one of these peroxy. And the peroxy acid is it this? Oh no, it's this. Epoxidation. It's stereospecific. I actually have no idea. I need to look at the answer for this one. My feeling is that we're just going to get something weird like this, but I have no idea. Okay, this is trans-2-butene. Oh, so this is what I drew. I don't know what this R is doing here. That R is weird, but yeah, that's what I would expect. It just forms the epoxide. Reaction of cis-2-butene yields an epoxide different than by reaction. Yeah, obviously. I'm not explaining that. Okay, epoxide reactions. That's a good comment, man. Yes, indeed. All right. Okay, so right, so as we saw that ethers cleave in strong acids, epoxides probably will too. So acid catalyzed epoxide opening. Epoxides are cleaved by treatment with acid, just as other ethers are, but under much milder conditions because of ring strain. Yeah, so they don't even need a super strong acid. Okay, that makes sense. Because of ring strain. Okay. Dilute aqueous acid at room temperature is sufficient for facilitating the hydrolysis of epoxide to give 1,2-diols, called, wait, vicinal glycol? Why do they call it a vicinal glycol and not just a vicinal diol? This is dumb. I'm just going to call it a vicinal diol, because that's a way better name than glycol. If we just Google glycol, what does that even give us? Because this is not even the most common thing that you get when you look up glycol is not even a vicinal diol. So this is stupid. The epoxide cleavage takes place by SN2 like backside attack. Right, that's right. So you have this sp3 whatever tetrahedral type of thing. So you have to do this but the thing is this is secondary. But whatever. Hydrogen comes in or oxygen attacks. Interesting. Okay, yeah, that's how we get this diol. Okay, so this gets pertinent. All right, I'm gonna draw this reaction because I actually like this reaction. This is cool. I just hate when I have to draw stereochem wedges and dashes. I just hate that, but it's chill. All right, so we add acid. So first off, the main point is that epoxide opening is easier than normal ether cleavage. So here this oxygen is going to attack a proton on the acid. And we're going to get this epoxide. And oxygen's now positively charged. We get these hydrogens here. And now what happens is we're going to add... No, now what happens is just a water molecule comes in and backside attacks. This pushes the lone pair onto oxygen. And we get a trans-vicinal diol. Because, see, what happens here is you get an inversion of stereochemistry. This is going to push the H out. And we also have what is it called? Oxonium? Yeah. In general, oxonium is oxygen with 3 bonds at a positive charge. Okay. So we still have oxonium. And then just water just comes and takes a proton. And we get a trans-vicinal diol from the ring opening. Trans 1,2-cyclohexane diol. I would call this, I like the new name, which would be trans-cyclohexane 1,2 diol. But whatever. Why does this happen again? The thing attacks and it bridges it. Bromonium bridge. Right. Epoxides can also be opened by reaction with acids other than H3O+. I kind of hate when they do this because, like, what does that even mean? If anhydrous HX is used, for instance, an epoxide is converted into a transhalohydrin. Oh, interesting. Cool. Okay, let's just start with the epoxide. So we react the epoxide with HX, and this thing attacks this, and this thing attacks this, and this goes like this. So then we're left with oh man. That comment got me laughing. That's good. Alright, the regiochemistry of acid-catalyzed ring open depends on the epoxide structure and a mixture of products formed. Oh yeah, so that... Well, no, actually, this is counterintuitive to me, because I would expect steric hindrance to be the main problem here. Oh yeah, I would. Yeah, you would. But there was something weird. Yeah. Like, why? This seems like totally counterintuitive. If this is adding to the more substituted and what? Alright, let's see. They're explaining. The regiochemistry of acid-catalyzed ring opening depends on the epoxide structure, and a mixture of products is often formed. When both epoxide carbon atoms are either primary or secondary, attack of the nucleophile occurs primarily at the less highly substituted site, an SN2-like result. When one of the epoxide atoms is tertiary, however, the nucleophilic attack occurs primarily at the more highly substituted site, an SN1-like result. Because probably what's happening... Yeah, okay, I get it. Alright. Because what's happening is that this thing is so, like, able to give up this electron density that's actually opened up, and it's got a pretty strong partial positive charge, and it's like almost a carbocation. So at that point, then okay, Cl attacks. Thus, 1,2-epoxy propane. Oh, is that what this is? 1,2-epoxy propane. Yeah, okay, cool. 1,2-epoxy propane. Let me write that down so that I remember the names of this thing. Okay, so this is a really interesting result that I don't have time to exactly write out. The mechanisms of these acid-catalyzed epoxide openings are more complex than they initially appear. They seem not to be neither purely SN1 nor SN2, but instead to be midway between the two extremes and have characteristics of both. For instance, take the reaction of 1,2 epoxy, 1 methyl cyclohexane. Let me try to write this down. I know that they're going to have it, but let's see if we can do this. So first off, we start with the main thing, which is cyclohexane. We have a methyl, and then we have an epoxide. With HBr. The reaction yields only a single stereoisomer of 2-bromo, 2-methyl cyclohexanol. 2-bromo, 2... Wait, what? Okay, so we're adding the HBr, so this thing gets protonated, and then this thing... This is going to be tertiary, so I would expect this thing to SN1 attack. And SN1 does not do inversion of stereochemistry. No, I think SN1... The thing about SN1 is that it gives you a racemic mixture, kind of. I think. We gotta see the picture. So, yeah, bromine attacks here. SN1 like does not mean a fully free planar carbocation intermediate. The thing that's so weird about this OChem is that it's like there's a lot of qualitative stuff in it, and you have to navigate it. I would say that's probably the most frustrating and probably the most interesting part of organic chemistry is the lack of solid ground. You know, like electromagnetism. You've got a great solid thing. You can always go back to the foundation. And here it's like shifting ground. I mean, there is some pretty strong ground once you get a hold of things, but it's still very loose, and finding your footing is challenging. I'm only in quarter 2, but I really am interested now in taking a biochem class. You know, like, I don't know, like I was looking into some ways that plants do like biochemical synthesis, and I was looking at it, and there's an enzyme, and it said this enzyme is a decarboxylase, so it performs a decarboxylation reaction. It's like, whoa, that's cool. What's up with that? Okay, I don't actually care. I mean, it's like, it's fine. I'm fine living with the fact that it does a backside SN1. Alright, predicting the product of epoxide ring opening. So here, because it's like secondary, I would assume that actually it's gonna SN1 from this side, and yeah, like clearly that's what's gonna happen. All right, how much more do we have? I think that might be it. I don't know what crown ethers are. Whoa, that's freaky. All right, so let's just do these problems, and then we have one kind of section left. All right, so predict the main product. Okay, I got it. This is 1812. The year was 1812. So because this right side is tertiary, we're going to say that first the oxygen is protonated, Cl takes the lone pair. Cl is then going to SN1 attack, but apparently from the backside, onto the tertiary. So then we're going to get cyclohexane, then this thing is an OH, and then this thing is going to be a dimethyl chloro thing. Right, this is my prediction. Part B. Right, here we go. We have an epoxide. Whoa, this is a freaky epoxide. It's like on the ring. I've never seen this before, I think. That's weird. So because this one is going to be primary, and the other one is tertiary, so we have a tertiary and a primary. That one I could go either way. I think that this one's pretty 50-50 on whether or not where the hydroxyl and the chlorine ends up. Let's see. What does the book say? So this is 1812. So yeah, this one was obvious. So they're saying because it's tertiary, that the oxygen is going to be kind of like way over. And then chlorine just comes and attacks. And so you have a methanol thing. I mean, I'm okay with that, but I think that it's probably way more mixed than. Okay, I guess in this is one of those cases where you just learn the rule. How would I prepare the following diols? This is hard to see. It's always hard to see these things. Alright, so this is a cyclohexane with a methyl and a trans diol. Okay, so let's draw this thing. Okay, so the methyl. So wait, I want this going. Okay, this is going down. This is OH. So this methyl is going up. Then we have an H, and then going down is an OH. So we have the trans diol. If we want to make a trans diol, we need to make an epoxide. And to make an epoxide, we use metachloroperoxybenzoic acid, MCPBA. Okay, so I'm pretty sure that we just do this from MCPBA to get a transdiol. This gives us the epoxide, right? Shit. I actually don't remember. First you add MCPBA, then you add acid. Because this is going to give you the epoxide. Then the second thing you do, from but it needs to add to an alkene, right? So I need an alkene. So what I would do is I would take an alkene. Then I would add MCPBA into the epoxide. And then I would add acid. So what acid does is we protonate this, then we have water attack, then we have a base take the thing. Okay. So let's see, was I right? Oh, wait, are they sin? No, they're actually sin. It's always so confusing to me. But yeah, that is sin. Notice the relationship of the hydroxyl groups in the two diol. In diol A, the two hydroxyl are cis. Or I said sin, cis diol. Indeed, they're trans. Since ring opening of epoxides forms trans diols. Oh yeah, so the true answer to 1813 is not. So we have a, let's see, wedge OH and a wedge OH. And then we have a CH3 H. So this is a cis diol. And so to make cis diol is OSO4 in pyridine. Coming. All right. I think I'll just start it up again.